Good afternoon, everyone. I'm Aruni Abeywickrama. Today, I'm going to present on cyclic behavior of soft clay railway subgrade prone to mud pumping. I will give you a brief introduction to the study, then the experimental study, numerical model, and some industrial benefits. Due to the rapid population growth and economic pressure, railways have become one of the key elements in the national transport system in recent decades, especially in Australia. Site investigations show more than 300 locations of bomb holes along the rail track in New South Wales. This is some of the photographs of mud pumping sites taken along the South Coast Rail line. These investigations found that the subgrade soil softened and fluidized under heavy rail loads, resulting in upward migration of fluidized fine into ballast. Moving on to the outline of the study, let's see the problem. Several incidents and issues have caused in Australian rail network due to derailment, especially in heavy haul tracks. From investigations, it has found that the major cause for these issues is the subgrade fluidization. Then a site investigation and sampling was done from a mud pumping site in New South Wales. Then understanding the mechanism of subgrade fluidization and investigation of mitigation measures. Past studies and from investigations of soil works in this study, it is clear that mud pumping usually occurs in silty clay soil with low to medium plasticity, as we can see in this figure. The plasticity index of soil was 11%, which indicates a low plasticity. The particle size distribution of the soil compared with the soils from other mud pumping sites in past studies is shown in this figure. This analysis shows approximately 55% silt content, which is within the range of previous mud pumping soils. A series of cyclic fracture tests was conducted under undrained condition and partially drained condition with the use of a scaled down PVE. The soil collected from the site was kept in a humidity control room for 24 hours to ensure the uniformity and consistency. And specimens were prepared using the moist stamping method. The specimen was then saturated using back pressure saturation with an effective radial stress of 10 kilopascal and a back pressure of 400 kilopascal. Kempton's B value was checked to ensure that the specimen was fully saturated. After saturation, the specimen was consolidated anisotropically to simulate the in situ subgrade stresses. During the consolidation, a mean effective stress of 24 kilopascal was maintained. In order to model the cyclic stress state induced by the passage of trains in the field, a stress control loading scheme was adopted. A cyclic load with a sinusoidal waveform was applied on the specimens under undrained condition. Cyclic stress ratio, which is defined as the ratio between the applied deviated stress and twice the confining pressure, was used to represent the imposed axle load. Loading frequency was varied from 1 to 5 Hz and CSR varied from 0.2 to 0.8. Cyclic load was applied up to either 50,000 cycles or 5% axial strain. Let's move on to the experimental results of undrained test. The first graph shows the variation of residual axial strain development under undrained condition for varying cyclic stress ratios. The specimen does not fail under CSR of 0.2, where the specimen remains stable under a cyclic load below the critical value. The results show a gradual accumulation of residual axial strain before reaching a constant value. For CSR greater than 0.2, the specimen could not withstand the applied cyclic load as the residual axial strain rises rapidly at a larger magnitude of excess or water pressure. The larger the CSR, the magnitude of the residual axial strain. The second graph shows the effect of frequency on the development of axial strain under undrained conditions. Larger frequency results in smaller level of residual strain given the same number of cycles. We can see a photograph of the fluidized specimen. The top of the specimen is slurried and found more fine particles accumulated at the top with the moisture. From the graph of the deviated stress versus axial strain, we can see that, there's a drop in the deviated stress in the fluidized specimen. The behavior of the excess water pressure with the number of cycles for varying CSR and frequency was same as the axial strain. Regardless of the CSR, with the number of cycles, the excess water pressure increases under undrained condition. In the stable specimen, the excess water pressure increases gradually up to a constant maximum. The excess water pressure of fluidized specimen increases rapidly and reaches to a mean excess water pressure ratio of 1. Mean excess water pressure ratio is the ratio between excess water pressure and the mean effective confining pressure. Rising excess water pressure causes loss of shear strength and stiffness, resulting subgrade fluidization. An empirical model which shows a relationship between excess water pressure ratio and CSR was developed using the experimental results and validated with previous studies. Effect of cyclic loading on degradation of stiffness is analyzed. With the number of cycles, the degradation index decreases. Degradation index is defined as the ratio between the resilient modulus in the nth cycle to the resilient modulus in the first cycle. It was observed that there is a rapid drop in the stiffness after NC, the critical number of cycles at which failure starts to occur. The stiffness degradation is higher for lower frequencies. Based on the experimental results, an empirical model was developed to capture the initial stiffness degradation. A series of laboratory experiments was conducted using a scaled-down PVD, a prefabricated vertical drain, to simulate partially drained condition in railway subgrade. It was observed that the development of excess power pressure is decreased with the use of PVD. Higher excess water pressure occurred under undrained condition, under zero volume change, and under the partially drained condition, a volumetric strain was observed due to the dissipation of excess pore water pressure. It was clear that prefabricated vertical drain assisted in dissipation of excess water pressure and mitigate the loss of shear strength and stiffness. This Thus, the use of PVD in railway subgrade prone to fluidization would mitigate fluidization by dissipating the generation of excess forward pressure. A finite element analysis was conducted using Plaxis 2D to simulate the cyclic loading on railway subgrade. From FEM analysis, also it was observed that excess water pressure accumulated under undrained condition with the increase in number of cycles. FEM analysis also conducted under partially drained condition with PVD. It showed how excess water pressure development is reduced with the dissipation through PVD. Here are few concluding remarks and industrial benefits. Low to medium plastic soils, for example, plasticity index 10 to 30% can be vulnerable to fluidization and the associated mud pumping. Trains with high axle loads passing through vulnerable areas can cause mud pumping. Generation of high excess power pressure under repeated train loads is the major cause for subgrade fluidization. Excessive deformation of rail tracks occur due to subgrade fluidization. PVDs can mitigate the subgrade fluidization by dissipating higher excess water pressure. And the money that has to be spent on rail track maintenance due to mud pumping can be saved by introducing cost-effective preventive techniques. When soil is improved, safe operation of trains with high axle loads can be established. Thank you.